Okay, hello everyone, and welcome to the civil seminar. Today we are very pleased to have Dr. Ali Behrangi, who is an associate professor in the University of Arizona. So just to give you a quick background of Dr. Behrangi's work, he has several years of experience analyzing satellite data sets. He has been involved in the development and the analysis of satellite-based high-resolution multi-sensor precipitation estimation algorithms, and as well as the diagnostic evaluation, uncertainty analysis of precipitation products like infrared, microwave, radar, and extreme weather event analysis, as well as hydrologic simulations. So in recent years, he has been focused on the remote sensing of precipitation in the cold regions using a suite of different types of satellites like CloudSat, GRACE, as well as reanalysis and other observations. So Ali has been a member of several NASA science teams, including the NASA Energy and Water Cycle Study, NEWS, as well as GRACE, and he's also the member of the International Precipitation Working Group, as well as other very high-profile panels like the WCRP, GEWEX, or GEWEX. I always have a problem for saying the correct name. Ali received his PhD in 2009 from the University of California, Irvine, and after that he did a postdoctoral research at Caltech from 2010 to 12. And he continued as a research scientist at NASA JPL for 6 years. Then in 2018, he joined the University of Arizona, as he's currently working there. So Dr. Behrangi has received many awards, including the NASA New Investigator Award or the Program Award and the NASA Early Career Achievement Medal, as well as many other very prestigious awards. So it's a really great pleasure to have him with us to learn about all his interesting research works related to satellite data and how we can use them to advance our predictions, forecasting of extreme events. So with that said, Ali, the stage is yours. Thank you.
Thank you, Reza, for a nice introduction. I'm going to share my screen, and I'm, yes, so everything is fine, right? Okay, I really appreciate the opportunity for me presenting some of my research topics in front of audience in Western University, and a very interesting name, London City, which I, when I was searching for it, I was thinking, oh, is UK or is Canada? So I was searching for the local time, and it gave me like, some time that it's basically was not necessarily the London that we know in Canada. Anyway, thank you so much for letting me present my work. My topic is cold region precipitation estimation, challenges, progress, and opportunities. For this topic, I'm demonstrating how we can reach out to diverse data sets and science communities to solve some of the problems that we have. In this particular case, the cold region precipitation, which is a challenge. I'm from University of Arizona, and I have joint appointment in 3 different departments over there as associate professor. So just let me start with the understanding why it's important to estimate precipitation from space. The map that you see is just demonstrating the location of gauges and density of gauges, in fact, at different regions of the world. You see that many places we have very sparse data sets. Over US and Europe, we have a better coverage. But if we want to do some hydrologic analysis, we need to go to a basin scale. So We go to US, where the density of gauges are among the best. And we focus in a basin, we zoom in, and we get to this basin, which is 1,500 square kilometers. This is a typical size basin. And I put a yellow box there just to represent the size of a typical university, so you have a better understanding of scale. 2 gauges in the basin is very insufficient to give us the distribution of precipitation, spatial distribution of precipitation. If you live in places like Arizona, your neighbor can get rainfall, and then 2 streets above you may not get rainfall. And that's because the storms coming in different lines and directions, and you may not get it. So 2 gauges are definitely not sufficient for hydrologic assessment. The number of in-situ measurements are also decreasing because of many reasons that I'm not going to go through that. But we are not going to have more in-situ data in future. That's the trend that we see. In terms of temporal sampling for hydrologic application, I just show a cartoon here. Assume that the blue line is your storm. T+2 starts, and then T+4 hours reaches the maximum, and then it dies after maybe 7 hours. Another storm may start like 30 minutes after the time, and then after 2 hours finish. So you have kind of a very short scale or short time duration for that storm. So if your observation is every 3 hours, the amount of information that you can get from a 3-hour sampling is just demonstrated by the red line, which is basically connecting the 3 hours observation. So as a result, you can get a lot of overestimation or underestimation because you don't have enough temporal sampling to capture the storm. Sometimes you can even completely miss the storm with every 3-hour observation. So we need a higher temporal sampling observation for hydrologic assessment and capturing the storm. Now, if we look at the satellites that are available for us, well, I hope the movie should work. This should work because this is my computer. Let me go to this mode, maybe. All right, I don't know why it doesn't work, unfortunately. All right, if you go to the stat, I wanted to show a constellation of sensors that working together to produce some beautiful images of global coverage of precipitation observation, but apparently it doesn't work. I don't know, maybe because of within the Zoom doesn't work. I don't know. There is another capability that the satellites provide us, and is basically it can go through the storms and look at the 3D structure of the storms by satellites. This is something that in-situ data cannot give us because in-situ data are just looking at the collection of precipitation, but they don't basically monitor the structure of the storm. We can get the structure of a storm from satellites. We have type of satellites we call geostationary satellite, and as you see, they can observe 1/3 of the globe each time. And the reason why they can see such a full disk is because they are located at 36,000 kilometers above the Earth's surface, and they are able to cover a wide area. They can provide us with sub-hourly images and resolution of 1 to 2 kilometers. So it's very good to monitor the system, but what they provide us is basically, temperature of the cloud is not necessarily the precipitation rate directly. So we have to interpret precipitation rate from temperature of the clouds. The constellation of sensors that includes microwave observation and infrared eventually are being used in a concept called global precipitation measurement. And we can use all these sensors together to get better spatio-temporal resolution for our precipitation estimate from space. However, the challenge is these sensors are not necessarily distributed well in terms of time, local time observation. So sometimes you may not receive any satellite overpass for a few hours, and sometimes you may receive a couple of observations within 1 hour. So the distribution of sensors are not necessarily uniform through local time. So the challenge is what we should do when we have gaps between the satellites to observe a particular location. An example is here. So every 30 minutes, the gray area shows how much coverage you can get. So in order to cover the globe, you may wait for 3 hours. And then yet, this is the coverage that you get after 3 hours accumulation of all the sensors overpasses. And remember, when I showed you the 3-hour temporal sampling is not sufficient for hydrologic application. This is directly related to that challenge that you cannot necessarily produce a product by waiting for 3 hours to collect all the samples. In this case, you may need even wait for 4 hours to have a complete coverage. So this is not necessarily the best way to go forward. There are methods that are being used now. Seymour and IMERS products are using this kind of method, which basically says if you have a good observation of precipitation from one of the microwave overpasses, and then after maybe a few hours you have another one, you can kind of look at the location of the clouds from geostationary satellite, the one that is full disk I showed you. You can interpolate linearly between these two and then assume that that's going to provide you with the precipitation distribution. Well, there are many assumptions there, and it may not work always. For example, if your system at time T1 is here, and then at time T2 is here, and the system dies, and then eventually another system pops up. This is very typical for convective system. Then linear interpolation fails in this case. Also, if you have a system that is growing and then decaying, which is also very typical in convective systems, then linear interpolation is not going to give you this nonlinear relationship. So we need a method to deal with this. Plus, we don't want to wait sometimes for 3 hours after the present time to interpolate. We just wanted to get the near real-time information. So waiting for the second microwave to show up and interpolate between them is not necessarily very good for near real-time applications. Back in 2010, as part of my PhD dissertation, I came up with a method called REFAME, standing for rain estimation using forward adjusted advection of microwave estimate. And basically what it says is from that full disk image that I showed you, infrared temperature, you can understand the cloud development, because if the cloud gets colder, usually it's higher and is more susceptible for precipitation. So we use the combination of the infrared from geostationary and microwave interpolation to capture the growth and decay of a system. And that's eventually published in a paper called REFAME in Journal of Hydrometeorology. And it gave me also NASA fellowship that opened up a lot of opportunities for me after that. This is an example of the operational version of this product and is run in UC Irvine. This is basically providing 30-minute observation at 8-kilometer resolution. Well, all of these type of products are very useful because having graded high spatial temporal resolution product can have a lot of application. Precipitation is driver for many, applications: flood forecasting, drought monitoring, landslide forecasting analysis, even health-related issues. So having precipitation, accurate precipitation at good temporal and spatial resolution is very important. Well, this is just an introduction to why precipitation is important, but what I want to focus today is mainly cold region precipitation. Two reasons for that. One is your location is fairly cold, so I wanted to focus on the cold region precipitation. The other thing is this is a very big challenge, is a remaining challenge for precipitation community, because measuring precipitation, snowfall over cold regions is very difficult. And so basically, just a quick introduction. You know, anything high latitude, high altitude, we call it cold region because they are cold. The problem is we have the highest precipitation uncertainty over these regions. Importance is huge because of eventually when we calculate global water budget, we need to have a good assessment of entire precipitation. About 30% of global precipitation occurs over a 40-degree latitude, so it's important. Our mountainous region, high altitude regions, about 1.5% of global land precipitation occurs at elevations greater than 6,000 feet. There are growing interest for a cold region precipitation estimation because, for example, our mountainous area, that's usually a source of water for populations to use. So it's important to understand how much precipitation or snowfall ends up over a mountain. The challenge is we have to deal with very difficult types of precipitation. That means light rainfall, drizzle, snowfall, and especially all these precipitation over frozen land, which is giving us a confused signal when we from to this signal of ice particle in clouds, and that makes it very difficult for us to separate precipitation from the background sometimes. And of course, we have limited observation from ground. So over cold regions, people don't install much in-situ data. The sensors that we use in satellite, in remote sensing of precipitation, they have a lot of difficulties. And some of them, as I mentioned, is emissivity over surface, confusion between snow on the surface and snow in the cloud or ice in the cloud. Dry atmosphere that is typical for cold region. Also insensitivity of sensors to small droplets and snow particles. These are very small. These are small particles that can cause problem for detection. And okay, and problems like problems that we have with clutters over mountainous regions are also contributing to these challenges of satellite precipitation estimation over cold regions. Gauges also have a problem over cold regions. When we have snow, they may undercatch precipitation or snowfall. It's important to correct it for gauge undercatch due to the effect of wind and capping. As you see, like we cannot measure necessarily snowfall very well, and we have to correct for them. And unfortunately, methods for correcting gauge undercatch are uncertain. So a lot of people think that in-situ data are perfect. The reality is not. They are not perfect, and they are called rain gauges and are being used to measure snowfall. They are not designed to measure snowfall. So the uncertainty in measuring snowfall and light rainfall is sometimes significant from in-situ sensors. So we cannot trust them fully, unfortunately. So that's another challenge that we have. Plus, as you see in the map, they are very sparse in cold regions. There was a discussion in BAMS. So how well do we measure snow? And if you read the papers and look at it, you can see that the answer is not so good because of the problems that we have. But things are getting better. Some WMO campaigns are like SPICE are trying to develop better relationship for gauge undercatch correction. But the type of gauges are very different from one country to the other country. We don't have a good record of different types of gauges, and also when they switch from automatic to from manual to automatic or things like that. It's very complicated. So eventually we have a lot of uncertainties with in-situ data as well. Now, these are like the, kind of the numbers here from 1 to 3 are the gauge undercatch correction coefficients that you should apply to measurement at each gauge in order to correct the value for snowfall, for example. So if you measure 10 millimeter per day, you need to multiply by 3 to get something realistic in terms of correction for gauge undercatch. That's huge. And if you don't have a right method to do that, you're off significantly from reality. So these are the two methods, like one correction method suggested by Leggett's, the other one correction suggested by Fuchs. They can be 50% different. So guess what? You apply a correction factor, 50% different, your result will be very different. So what can be done? We know that there should be consistency between various observational water cycle components. So bottom line is we have to make sure that it's fitting within the consistency constraints that we have for earth science as a whole, or water cycle as a whole. The other thing is we have a lot of other disciplines or fields that may provide us with information that can be used for precipitation estimation. So we try to use these two items in our analysis, kind of different from what people usually do. We also reach to other communities, like there is a sensor called CloudSat that is really designed for cloud measurements because it's so sensitive to very small particles. But it turned out this satellite is very useful for capturing light rainfall and drizzles and snowfall, because it's very sensitive, and most of the current precipitation sensors are not able to capture these kind of precipitation. But CloudSat, which was designed for cloud studies, can capture that. So we published a couple of papers demonstrating how CloudSat can be useful for precipitation measurement in cold regions where we have a lot of drizzles and snowfall. And although there are some definite benefits for using CloudSat, there might be some challenges too, because, for example, there is a clutter issue that we cannot monitor the lowest 1 kilometer above the surface because of the signal confusion. But in many cases, we can still use a lot of good information from CloudSat. With CloudSat, we could come up with a distribution of different types of precipitation, different phases of precipitation, across the latitudes. So the red one shows the total precipitation distribution, just occurrence of precipitation from minus 80 degree or 80 south to 80 north. You can see how precipitation occurrence is distributed. A lot of precipitation occurs in Southern Ocean, over Southern Ocean, a lot of them over the 60 degree North Ocean. And also this is the land. And you can also see the snow distribution. So a lot of precipitation in general happens as snow in around 60 degree latitude, and this is the total precipitation. This is snowfall, this is rain, and this is mixed phase. So this distribution can basically came from CloudSat. Before that, we did not know exactly what's going on. We had limited observation from gauges, but now this is the first sensor that can be sensitive to all type of precipitation precipitation phases. So we could have maps like this demonstrating different phases of precipitation. With that analysis, we demonstrated how much different sensors in the constellation of precipitation measurement, the constellation that I showed before, how much precipitation might be missed. So we showed these red parts that are missing like 40% of the precipitation occurrences, and this is the amount. So we're missing a lot of precipitation, for example, over ocean in general. Just by using CloudSat information, we could capture that. So we need to work on these kind of situation. We don't want to miss a lot of precipitation, because eventually the water budget analysis and energy water budget analysis globally requires us to have a very good estimate of total precipitation. Back in 2012, I combined CloudSat with another sensors called TREM, Tropical Rainfall Measurement Mission. TREM can capture mid and intense precipitation rates, medium and intense precipitation rate, and CloudSat can capture the light part of it. So we combined these two instruments and came up with the total distribution of precipitation over the globe, from very light precipitation and snowfall all the way to very intense precipitation. And we use that product to assess different products in general. We call this product MCTA, standing for Merge CloudSat TREM and AMSER estimate. And these three sensors went into this estimation. So the red color, the red line that you see is our estimate. The green one is the Global Precipitation Climatology Project that probably you have heard about it. And, and the black one is another product, famous precipitation product called CMAP. For the first time, we see there is significant differences between what we think is the truth and what the products provide us. There is a big difference around 40 degrees. So we think that we're gonna have more precipitation. And there is a big difference around 60 degrees south, which products like GPCP are significantly demonstrating higher precipitation amount. So this is kind of a good example of how new technology can help us to gain more insights about something that we did not know before, and now we can focus on the differences more and more. CloudSat is a new technology. It just showed up in 2006. The GPCP product started back in 1979. So the new sensors can provide insights about what's going on, and then we can focus on the improvement in future. So the differences are shown here. I'm not going to go through the detail because I have too many slides. But this paper is published in 2014, an update on global distribution of oceanic precipitation, if you're interested. This is the paper. Recently, we had a GPM launched in 2014. It's a little bit, provides us a little bit improvement over TREM, and also expands the region of coverage from 35 degrees to 65 degrees south and north. So we updated MCTA with GPM, and now it's called MCTG, standing for Merge CloudSat, TREM, and GPM. And we use this now to improve some of the existing products, because now we have more insights about the distribution of precipitation using this kind of product. An example that I want to show you here is very interesting. The GPCP, standing for Global Precipitation Climatology Project, shows this kind of precipitation, wintertime precipitation accumulation. CloudSat, I mentioned, is a good sensor for snow and light precipitation, shows this image. The challenge was which one is correct, because CloudSat still is a satellite product. We don't have a good validation for it. We don't have in-situ data that are very well designed in this region, cold region. And we don't know if really this is the right answer or not. So we thought about this and thought maybe we should use another property of snow. And by the way, this is just winter, so it's all snow. We thought maybe we should reach out to another property of snow, which is the mass of a snow. Snow is very massive. 10 centimeter snow over a 300 kilometer by 300 kilometer area can give us a weight of 3.6 billion ton. So it's a very massive feature. So if we use that feature and we have a way to monitor the mass of snow, we can provide some insight about accumulation of snowfall. We know that GRACE is a sensor that is measuring gravity and mass change. So we reach out to GRACE community and discuss things with them, and it turned out that GRACE can help us in this situation. And I became a science member in the science team of GRACE science team, became a GRACE science team member because of this kind of project. So after interacting with them, we came up with solution for it. Basically, GRACE can provide us with the mass of the snow and it can be turned into the snowfall accumulation. Just putting it in the water budget equation. Sublimation, we can count for it using reanalysis. It's not a big number. The lateral flow is negligible in winter when everything is frozen. ET is very small or negligible. And then whatever is fine is remained is changes of storage or mass is equivalent to the amount of accumulation of precipitation. We restricted the temperature in this case to -1°C, so anything there is frozen and no melting happens. So we kind of confirmed CloudSat result using mass change analysis. So this is an example how different communities can work together to solve some of the issues that we have. We also did some analysis by converging the water vapor from, just converging the water vapor through this equation give us total precipitation minus evaporation. And in fact, the overestimation that we see in GPCP, if we see this overestimation, is also seen when we use the GPCP in the convergence of water vapor. So we can look at the atmospheric analysis, we can look at the mass and mass change analysis, and we look at the snowfall and CloudSat product. And all of these can give us insight about the snowfall accumulation. In fact, we could use the mass analysis to also vote which undercatch correction method might be more consistent with our observation. In this paper, we showed that using GRACE, we can suggest that maybe the method of Fuchs for correcting a gauge undercatch could be the better approach, at least in terms of consistency with water budget components. We extended some of these analyses to over Tibetan Plateau, where we have significant challenges with quantifying precipitation accumulation. We have to stick with the large region because GRACE is not going to provide us high resolution. So we had basin scale analysis, and it shows that in wintertime, we miss a lot of precipitation or snowfall from other products. And GRACE, the red line, shows that how much precipitation or snowfall is missed. And this is like distribution of precipitation from different products. And this is what we think that should happen based on GRACE analysis. So there is a big gap that we need to work on it. I'm not necessarily saying GRACE is perfect, but I'm saying that there is an insight that there is a big gap in wintertime in quantification of snowfall. So we need to work on this area more to make sure that what we're measuring is good. We can do the same thing over different basins and using stream flow, just close the water budget in the basin scale and use a stream flow in this case. And in that case, we see that some of the gauge undercatch correction methods are way off. And this is an example where GPCP shows a lot of snowfall, where the reality, or at least GRACE perspective, is showing much less. So we could use mass change also to, and runoff to get understanding of the precipitation and snowfall accumulation, bottom. Similar way can be also used in Antarctic. Antarctic is absolutely very difficult region, right? So we reach out to other communities that they measure ice flow. So all these ice sheets are flowing to ocean. They have a fairly accurate estimate of ice flow into ocean. Similarly, we can we have basins in Antarctic. So we know exactly how much ice flows into ocean in this basin and how much in this basin and how much in this basin based on the work of Alex Gardner. So we team up on this and calculated the amount of snowfall in each of these basins together using mass changes as well as ice flow. This is the result. So these are the mass balance approach for 2008, 2015. Each color demonstrates the value of a snowfall accumulation. And CloudSat is also there, providing us some insight. We have reanalysis product also there. And then we have some GPM products that are way underestimating at the moment. So this approach also provides us with some quantification of precipitation from completely independent approach. And now we have enough food to discuss and talk about the differences and do scientific analysis and at least understand what are the differences among different products when we talk about consistency of observations. We can also reach out to snow water equivalent measurements because, you know, in concept, the snow water equivalent should be equivalent to the amount of snowfall accumulation. There are products that are generated by community. One of the good products is developed in the University of Arizona using just in situ observations and kind of a smart interpolation of in situ observations. We put different products, you know, GPCP, Prism, you know, reanalysis, everything. So we selected the region that is completely frozen, no melting happening, and start to accumulate precipitation from all different products. And we assume that SUI product that is carefully put together is the reference. And then we can also have grace observation, you know, as I mentioned this. So we can have all sorts of different observation of a snow accumulation and then understand the differences and at least kind of check the consistency and see how much uncertainty exists in our current analysis of snowfall and snowfall accumulation. So this type of analysis looks like interesting because now we can have less or more confidence about our observations and point out to some of the areas that require further research. You know, California is, you know, highly dependent on water resources or snowfall over the mountains as the source of water resources. And they have a plane called the NASA Airborne Snow Observatory, which measures SUI at 50-meter resolution or even better. We used a basin that is well covered by this plane and then use the SUI measurement or snow water equivalent measurement and compare that with the satellite snowfall products and demonstrated where are the problems and where, you know, it turned out we are missing a lot of snowfall over this region by satellite products because we think that this product is very accurate as it's compared with the snowtail and other things. So this is a way to assess precipitation at spatially because we have few snowtail to measure to assess precipitation products, but using observation from airplane like this, we can assess the product. So this paper was published in Water Resources Research if you're interested in. Well, another area that is very, very difficult is how much snow happens over sea ice. I mean, we don't have any in situ data, or we have very, very limited in situ data to quantify if our satellites seeing amount of precipitation over this region is correct or not. Well, we needed another community. So we, you know, when I was at JPL, the good thing is I had access to a lot of different groups. I reached out to cryospheric scientists and said, do you have any ways to measure snowfall over sea ice? And I was thinking they don't care. Who cares about the snowfall over sea ice? It turned out they care a lot because they want to calculate the thickness of the ice. So they need to know the weight of the snow on this, you know, on the ice, the sea ice, so they can calculate the thickness of the sea ice. So they had developed already methods to calculate the snowfall over sea ice. And we team up with them to do this kind of analysis. In fact, 1/3 of the, you know, 2/3 of the ocean area, pole one of 50° north during the peak season or the coldest season is covered by a sea ice. So it's a huge area. And if we don't know how much snowfall happens in that region over this region, we are not able to quantify global precipitation correctly. They had a, you know, mission like ICE, they call Ice Bridge. It has 2 radars and somehow one sensor, well, they have 2 different signals, but one sensor can penetrate into snow and stop at this interface between snow and ice. And the other one can just, it cannot penetrate into snow. So if we subtract these 2 signals, then we can get the amount of snow depths. And then with assumption about snow density, they convert it to snow accumulation or snowfall or snow SUI or snow water equivalent. We use that observation for assessment of our product. And there is a paper published this year about how we can use this kind of technology to assess precipitation over sea ice. And that's perhaps the only way that we can assess snowfall accumulation or precipitation over sea ice. The bottom line, what I want to say is we have a challenge called cold region precipitation estimation. We can look at it from different angles. When we look at satellite snowfall measurements from new missions, we shed some light on that. So the problem is much better than what we already had from limited in-situ data. Now, we have other missions like mass change mission, like GRACE, that can shed additional light and provide more insights. And then we have observations from like SUI measurements, snow water equivalent observations that can also provide additional insights. So eventually the dark red becomes lighter red, and we mitigate some of the problems by reaching out to different communities. So perhaps the next generation of products can collectively provide solutions to what seems to be difficult to achieve using a single set of instruments. The notion of I'm gonna stick with my approach and do my best to improve that type of single approach is probably not necessarily working anymore. We need to reach out to the community because eventually this is Earth as a system and everything should be connected. So we should really reach out to other communities to see what they have for us to solve some of the problems that we have. In fact, if we look at the decadal survey, which demonstrate the plan for the next 10 years of organizations like NASA, these three different methods are mapping to some of the missions that probably going to make it. The ACCP, aerosol cloud convective precipitation, is going to provide us with better precipitation measurement. We have mass change designated mission. That means that we're going to definitely have something like GRACE in future, built up and sent up. We have definitely have something about precipitation. And then we have another explorer. That means that if we have enough budget, we also go for another mission for snow water equivalent measurement from space. So the art is to connect all these concepts and come up with the best estimate. Now, I think I have a few minutes left, but I just wanted to emphasize that all of these are good, but how we can implement it, how we can use this kind of insight that we gain from analysis of different products and different missions. Well, luckily we got funding to use these technologies, these different approaches to improve high latitude precipitation for improving the GPCP product. So the title of the project is High Latitude Improvement of Long-Term Global Precipitation Climatology Project, GPCP Precipitation Products using recent NASA missions. And these NASA missions include GRACE, CloudSat, some of the CI stuff that I mentioned. And I'm directly working with all these good guys that develop GPCP from scratch. And I'm very excited working with them. So GPCP, if you don't know, is one of the few state-of-the-art global long-term precipitation products. It provides us with precipitation product going back to 1979, and is being used by community very widely. The citation of the original papers exceeds 6,000, and a lot of people are using it. The current product at monthly scale provides us with 2.5 degree resolution, and daily product provides us with 1 degree resolution. So in our project, we're going to improve this to 0.5 degree resolution because users want higher resolution products. So the version 3.1, which is going to be a new version and is already available, it just happened in July. So we released the product in July. So it's available for people to use. We will have already have the 0.5 degree resolution. So the MCTG that I discussed is merged class at TREM GPM, is being used to calibrate 2 other sensors, TOBS and AIRS, over high latitudes. The TREM combined climatology is also used for, tropical region, but my focus will be mainly in high latitudes. So MCTG is used as a calibrator of other sensors right now. Ice Bridge provides us with the information over sea ice. GRACE and ice flow is going to provide us information over cold regions. Antarctic, as well as Siberia and other places. So we are using all these sensors to assess what we had before and what we can do for future products. This is an example that the GPCP version 3.1 is now look like the red one. The old version is the green one. And you see the changes are just because of use of new technology and what we know maybe in light of CloudSat and GPM. So the distribution of precipitation over ocean has been changed in the new version. This demonstrates how spatially the changes are occurring. Mainly we have more precipitation over storm tracks in light of GPM mission that is able to capture intense precipitation better. And then we have kind of increase of precipitation around 40 degrees that I showed before, and decrease of precipitation around 60 degrees south a little bit. Compared to the typical sensors that are available on GPM, we know that they underestimate. So the new product has more precipitation over the high latitudes compared to the previous, compared to this one single sensor, because they have challenges getting the snowfall and light precipitation. So in light of CloudSat, we can add more precipitation into these locations. The variables available from GPCP 3.1 are sorted or listed here. There are lots of variables in terms of error and quality and other things that you can go to the website and look at it. The bottom line is over land, so far we see a slight decrease in precipitation amount, although our focus in the version 3.1 was over ocean. We see about 6.2% increase of precipitation over ocean because of the use of new instruments. And then overall, we see about 4.5% increase in global precipitation. And that's huge because think about it, every 1 millimeter per day is equivalent to 29 watt per square meter energy. So we are talking about imbalances in energy budget of the Earth, and precipitation plays a significant role to make sure that all the components in energy balance are calculated correctly. So this contribution is significant with respect to global energy and water cycle studies. The product is available from NASA website, Gas Disk. You can go there, type GPCP 3.1, and then it shows up as I show here. There are lots of documentations and you can read all the details there, and the references are also listed if you use the data for citation of the product. The last slide is concluding remarks. Well, large uncertainties exist in quantifying cold region precipitation amount and distribution. Current typical satellite data are not robust enough to provide us with trustable estimate. These are the gaps or challenges that we currently have. We reached out to other communities or measurements like CloudSat, GRACE, OIB, basically Operational Ice Bridge, CryoSat, IceSat, IceFlow, and SUI measurements to come up with guidance for further development of precipitation products over cold regions. This is a multidisciplinary effort and approach. For cold region precipitation estimation, diverse products across different fields can collectively provide solutions to what seems to be difficult to achieve using a single set of instruments. That's the message I wanted to convey, and I mentioned that before, but just for emphasizing, I mention it again. The next generation GPCP products will benefit from some of these observations. Thank you so much, and I end it up here by acknowledging my funding resources, 2 projects from NASA, basically.
Thank you very much, Ali. Very interesting and highly technical work. It's huge implications for hydrology, extreme analyses, and well, in this audience, we have people from different areas in civil engineering, like structural, wind, etc. But we all know that extreme events can affect all of us. So thanks again, very interesting. And I want to ask if the audience has questions, you can use the chat window or just unmute yourself and ask your questions. In the meantime, Ali, I have a few questions myself. I don't want to be asking very highly technical ones, but So my sense is that for cold region precipitation estimation, the feeling is that you have to use other sensors. You cannot just rely on precipitation sensors to do the reliable estimation of precipitation, which makes sense. What about other areas? Do these precipitation sensors do a good job in estimating precipitation in other regions or in warm periods? Or do you think for those you also need to look into other sensors, for example, look into just the runoff estimates or the groundwater estimates, etc.?
Well, based on analysis, over warm regions, near tropics, tropical regions, we are still in a good shape. Satellite products are perhaps providing a reasonable job over there. And that's because of the systems are very strong. The convective systems are providing us very strong signal that we can assess from, we can measure from satellite sensors. The shape of the systems are isolated. The height is directly related to the intensity of precipitation. And some of the relationship that we find in the tropical regions are easy to capture. It's not perfect. We require better sensors. We require better retrieval algorithms. But given the fact that intensity is significant in tropical regions, we have very intense precipitation. We have very good signals that we can use for retrieval of precipitation. And usually we don't have significant problem in those regions. As we get to a higher latitude, colder regions, light rainfall problem, snowfall problem are becoming a challenge for us. And, everything is relative, but in high latitude, we relatively have more challenges.
All right. We have a question from Clara, but before I get to you, Clara, one more question. For the iMerge program that you showed on your slides, as far as I know, they also provide the snow component of precipitation. Is it also based on CloudSat, or there is another way?
No, the iMerge currently only uses the microwaves to capture snowfall in high latitudes exceeding 60 degrees, a poleward of 60 degrees, because geostationary satellites are not giving us good quality images, poleward of 60 degrees. So anything poleward of 60 degrees coming from low orbit microwave sensors, and microwave sensors have a lot of problems capturing snowfall at this moment. I mentioned some of the reasons. Within the 60 degrees south and north, they use infrared for estimating snowfall over snow-covered area. And that's also is uncertain, but that's the way they do it.
Right. Thank you. All right, Clara, please go ahead and ask your question. Oh, can you hear me, Clara?
Yeah, yes, Mohammed, thank you. So my question was on the slide for the large values of and uncertainties and gauge undercatch correction factors. And my question would be first, why you chose like legates and Fuchs for correction factors?
Oh, I see.
Yes.
Well, these are two methods that are very popular in terms of their application. So, the legates product is used in the GPCP currently for correcting undercatch. The Fuchs method is used in GPCC, global, that's a gauge-based product. So these two correction methods are being used in two very famous products, and that's why we use them, because of the impact they have. Maybe there are other methods. I know there are other methods that maybe they are not operational. So that's why we didn't use it. But if you have some suggestion on the operational method that is being used, we want to include it in our assessment.
And one more, thank you. Why you chose 3 hours, and then you had mentioned about the 4 hours, like on temporal sampling as well?
Yeah,
just
so
in terms of observation. Sorry.
So this 3 hour thing that I guess you're referring to this one. So this is how the TMPA product, the version before IMERS, it's called TREM Multi-Sensor Precipitation Analysis product, or 3B42. This is the resolution that they provided because that's the way they had to deal with this kind of infrequent observation of microwaves. So they had to wait for 3 hours, collect them, and then fill the gap with infrared. They wanted to use microwave estimate as much as possible. So their product was 3 hours at that time. And even after 3 hours waiting, still they cannot cover this. So 3 hours probably is a trade-off between what hydrology is required. Always they want higher resolution, but there's a trade-off between what they want and what is possible. So they stick with 3 hours at the moment. IMERS now is doing 30 minutes by using the new technology or new retrieval method that I explained. So.
Thank you, Ali.
No problem.
Okay, questions? So with the trend that you see in advancements in satellite sensors and all these estimations, do you think in near future, there's a possibility that every analysis will be just based on satellite data and there will be no in situ measurements?
No, I don't think that's going to happen. I mean, always in situ data are important for us because they are measurements. There is a difference between word measurement and estimate. The satellite products are providing us estimates. That means that we cannot directly measure the amount. We just can't see signals like temperature of the cloud, some reflection from the hydrometers. So eventually, through retrieval, we estimate the precipitation. The ideal case, the ideal gauge should give us measurement that directly measures what's happening. So this gap between measurement and estimates requires both instruments. I mean, we need measurement to guide us what we estimate. And that's why I don't think in situ data, I mean, we always need in situ data for assessment and calculation of the products. But we need good in situ data, and we need to make sure that we can capture the snowfall correctly, and we can deal with the gauge undercatch problems. This is the challenge that we don't have it at this moment. Maybe fewer stations, but most of the stations are not equipped with the instruments that can do all these kind of correct measurements.
Yes, yes. Yeah, we were looking at some of these in situ data and in Canada, and you rarely can find any reliable one with a long enough data set over like the Nunavut or the Northwest Territories. It's a big challenge. Yeah.
Yeah, I mean, I'm really interested in collaborating with you guys. If you have some, good observations, we can either evaluate our products or we can, provide insights or guidance in your projects if you're interested in. So if you have some precipitation related in your region, I'm always interested to work with you guys.
Yes, definitely, definitely. We have a question from Chao Sheng. Thanks for your presentation. The freezing rain precipitation is one of damaging precipitations in cold region. Yeah, the freezing rain is a problem in cold region. Do you think the estimation of freezing rain currently also has large inconsistency among different data sets?
Correct. That's definitely a challenge. I mean, hail, there are methods that we use for hail detection and using some of the satellites. There are some advances happened. We can detect hails. We can also detect, frozen particle. What is the challenge right now is most of these snowfall estimates are coming based on temperature. So we estimate precipitation, and then we convert it to a snow or rain by looking at the temperature profile. Is not a direct retrieval of a snowfall or ice. We look at the temperature of the environment and decide if precipitation should be rain or snow. So there is a two-phase approach. But if you have a sounder or have a vertical distribution of temperature from the analysis, we can do some sort of analysis like that. We are not very mature, I should admit, we are not very mature in measuring the frozen precipitation falling on the ground. This is still a challenge for us.
And my sense is that for problems like hail, they mostly rely on radars, right? And ground estimates.
Yes, a radar, since it provides the vertical structure and vertical information, is very important. But people use sounders, microwave sounders, because they also have, they also give us information in the vertical distribution of precipitation, so they can also provide us guidance for hail detection. In fact, there are papers, at least I reviewed one paper recently that deals with that issue.
Mm-hmm. Great. And maybe it's my last question. So with these works, have you generated products specifically for Canada that we can use for research or application?
Well, we are focusing on high latitude. So Canada is one of those high latitude regions. So we are not necessarily just doing for Canada, but the new GPCP product is basically supposed to provide updated information over the high latitudes, including Canada. That's our next phase of the project. So previously we focused over ocean. Now we are focusing over land. And you know, if we can come up with a method to better correct for undercatch of gauges, I think that's going to be a good contribution to regions like Canada. We are looking at some region over Alaska right now by looking at the snow water equivalent and see how much information we can gain from snow water equivalent measurements, and how we can kind of compare our estimate over snow-tail regions. I don't know if Canada has a lot of snow-tail, but if you have some snow-tail, I'd like to work with you guys and maybe we can do something together.
Not as many as in the US, but yes, we do have snow-tail data.
Yeah, that's very important for us because that's probably the most accurate instrument to measure snowfall at the moment.
Yes.
So yeah.
Yes, very interesting. Thank you very much, Ali, again for for sharing all your works on this area. And I hope that in the future we will also have you again to update us on your progress and more accurate estimates of precipitation. Thank you again.
Thank you. I appreciate your time and effort.
Thanks. Thank you, everyone. And I hope to see you next week.